So, good morning everybody. So back to recursion. Yesterday we talked about recursion. We talked about the fundamentals of recursion, the meaning of recursion, approximately, in terms of mathematical proofs, induction. And then we talked about what happens when we do a function call. Recursion is no different than any ordinary function call. Is there a question from the online audience? Are there any questions? No? But somebody's microphone is on. I don't know who. Okay. So we talked about this. What happens when you do a function call? Since recursion is no different than any function calls, when we do recursive calls, we apply the same rules. Put your data on the stack and push them on the stack, and push your variables, arguments, parameters, and the local variables on the stack, and etc. We traced the stack and the program while we are doing the recursion, and then we said that this is just one way of looking at recursion. When we are writing recursive programs, you don't think about your stack, you don't think about activation records, pushing data to the stack and popping data from the stack and etc. You don't think about them. All you think about is these basic rules. Okay, if I am going to do this, where is my base case? Okay, the smallest problem that I can solve very easily. Okay, if I am going to do this right vertical, okay, what is the smallest, simplest problem that I can do? It would be a single-digit integer. I can do that very easily. I just print it out on the screen. Okay, if the problem is that's my base case. Otherwise, I will have to divide my problem into smaller parts. Okay, I am going to do it in a way that the smaller parts are very similar to, in fact, the same as my original problem, but they are smaller. And I can use this function again to solve that problem. That's what we are doing. If integer is less than 10, I just solved it and I return from the function. That's it. Okay. If it is greater than 10 or equal to 10, this is what I am going to do. I am going to say that, okay, print all the digits to the screen other than the last digit. This is what it does. And I'm going to print the last digit on the screen. Okay, I know that by doing this, I will hit the base case. I know that by doing this, I will hit the base case. That's how I make sure that induction works. Okay, remember k minus 1 thing. Assume k minus 1 works, and then show that for n is equal to k it works. Okay, so that's what I'm doing. Assuming that I divided by 10 works, okay, and I am solving the rest of the problem by doing this. Okay, that's what I did. So these three rules: base case, divide the problem, divide and conquer. Remember that one. Divide the problem into smaller parts. Okay, those smaller parts should be exactly the same as my original problem, but smaller. Okay, if it is not smaller, then I will not hit the base case. Okay. The problem should get smaller. If it doesn't get smaller while keeping the exact same problem, I will run into an infinite recursion case, right? That would be a bad thing. That would be a bad thing. Okay, so that's what we did last time. And using this idea, you can do many things. Whatever they tell you, you can write it in a recursive way. Some problems are very much suitable for recursion. Some of them are not much, but in theory, whatever you can do with loops, whatever you can do with other type of programming, you can do it with recursion. But sometimes recursion is a little bit more maybe recursion should be your second alternative when it comes to function type or the problem type. But for many problems, including especially including lists, or see, if you have a list, linked list like this, okay, there is a natural way to divide this list into two, okay. It is the first one and the rest of it, okay. Whatever you are doing, this is how you divide your list into two, okay. First part I can handle. The next part, it is exactly the same problem as the original list, okay, only smaller. So this is going to hit the base case, no problem. So if you have an array, if you have a linked list, stuff like that, recursion fits perfectly. Or you will see cases, and you did some of them. You have a tree, right? Like a tree. This tree, binary or, okay, 3 elements, doesn't matter. This is a tree with a root node. So let's say I am trying to calculate the depth of this tree. What is the depth of this tree? What is the depth of this tree?
4.
Yeah, 1, 1, 2, 3, 4. Okay, give me a recursive algorithm. Give me a recursive algorithm that calculates the depth of this tree. It is very easy. You say that for this node, root node, okay, call depth on your children, 1, 2, 3, get the maximum depth and add 1, okay. So I have 3 children, 1, 2, 3. I will call the function that measures the depth, that estimates the depth, that calculates the depth on these, and I will add 1. So this one will return just my depth is 1. This one will return 1. This one will say, I don't know what to return because I need to ask this to my children, okay? This one asks the children. This one returns 1. This one, I don't know. I am going to look at my children, okay? This one returns 1, so this one takes it, and 2, and this one will return 3, and this one will return 4, okay? So this problem, this whole problem, is very recursive. Why? Because the smaller parts of it, this one, this one, this one, and this red one, okay, they are exactly the same problem, three problems. And for 3, again, I have this problem and this problem, okay. For 2, again, I will have another. Well, I am out of color, but you know what I am, where I am going, right? This one. So for linked list and for the trees, recursion is perfect fit, because each of your children is exactly the same as you. They are only smaller, okay? So calculating the depth is very, very easy, or trying to find something is very, how should you search a tree? You just ask your children to search it, and they ask their children. And base case is very simple. It's just, if I am the root and I don't have any children, then that's the base case, right? That's the base case. Okay, so we talked about that. So where we apply the recursion, where we don't. Okay, so these are the rules, and I think we were talking about writing different types of recursive stuff, and we talked about this infinite recursion. Did you test this? Did you test this to get the infinite recursion? No? Nobody tested it? How about the online people? Online people, did you test this? Unfortunately, no. Okay, if you don't do that, I am going to do it. Let me make a new source file. Okay, int main. And this is what I am going to do actually. And I am going to call main. Okay. An infinite recursion case, right? Main is a function I can call the main, right? No problem. Let me compile and run this. Compile it. Okay. Without giving any name, it doesn't exist. Okay, it compiled it and let me run this. Is this run? Yeah. So I am running it. It is running and it is running and it is running. It should be. No, it did not. So it says I came. Yeah. So my program crashed. Okay. My program crashed after 6 seconds and 6.1 seconds. Okay. And it returned this value, whatever it is. Okay, it's a nonsense value. So it has crashed because it ran out of memory. Let me look at this. Okay, this is my memory, right? Now I am using, no, I don't want to do that, no. Let me see, yeah. Whoever using the most memory, I am showing it here. Now I am going to run this and, come on, where is my task manager?
On the upside. 4.
Where?
This is the job, first one.
Third row?
Fourth.
First row, fourth. And second row one.
How come I can't see it? You see it?
Second
It
row.
is yellow.
Second hocam.
Yeah. Okay, so maybe I should just do it this way. And this one is already crashed. Okay, and go to my div stuff and run it and minimize this and take this out. So it is running as okay. I couldn't catch it. I was going to show you what kind of memory it is using, but it is running too fast, and I can show you. Do this experiment yourself. So it crashes because this is an infinite recursion. It has to crash. Only one thing is there. Let me go to this tools and compiler options. I am going to add one compiler option -03. So I am going to optimize the code at the third level, very high level. So this is as much optimization that you can get. Compile it and let's run this. So it is running and running. We are going to wait for the crash. It is not crashing. Okay. So I optimize the code and it is not crashing anymore. So what's happening? It doesn't crash. This is a really infinite recursion. Let's go to the program. I will let it run, but it will never crash. Let me show you my program again. I don't know where that one is. I think it is under the, maybe this one. Console, is it done now? No, it is just still running. It is not done. Okay, it didn't crash. Tell me why it is not crashing. So you are never listening to me. Nobody is listening to me. When I joked about 80% of you are going to fail, it wasn't a joke. Yeah.
Combine to convert it automatically tail recursion.
Yeah, it is already a tail recursion case, right? It is already a tail recursion case, and compiler just noticed it and say that I am not going to use the recursive way of calling functions over and over and over again. Compiler recognized that this is a case of tail recursion, and it is just every time it makes a new main function call, it just erases the stack. Okay, it uses the same position over and over again because this is the tail recursion. Okay, so let me stop this, still running, and let me convert it to this one, +1. It is not tail recursion anymore. I am compiling with the optimizer again, O3, and run it, and in 6 seconds or whatever, it should crash. Or okay, compile it again so that it is a simple thing and it is doing some kind of optimization maybe. But if I didn't use that optimization thing, I would have obtained a crash. I think compiler is smart enough to see that this can be converted to a tail recursion case, since my programming function is too simple. Okay, so tail recursion, as I said, if it can be used, with your functions, you should try it, because compilers have ways of optimizing those kind of functions. And in fact, our compilers are smart enough to convert these kind of simple stuff to loop-based assembly programs instead of recursion. So do the right thing first. Write your program. If it is suitable, write your program using recursion. If you can write it using the tail recursion, then write the tail recursion. And don't forget to optimize your code using those flags. And the compilers will help you to produce fast code or the efficient code. Okay. So if I make this a little bit more complicated, compiler will not have any way of converting this to. Let me see if it is smart enough to do this, because there is no way this can be represented with a tail recursion. But looking at it, okay, you know that this is not meaningful. So let me run this. Yeah, this one crashed. I mean, it is not smart enough to. Well, I mean, that's not a meaningful. That's not a meaningful program anyway. Okay, and there is no way to convert that one to a tail recursion case, so it's going to crash. Okay. You had a question?
I was gonna say the previous version with +1, the cause of infinite recursion may have something to do with order of evaluation.
Well, whatever you do, whatever you change order of evaluation here, plus has to be done last. Okay. So if plus has to be done last, then it is not a tail recursion anymore. But you can rewrite this main function so that this function doing exactly the same thing. But remember what we did last time to convert one case to tail recursion? Where was it? Somebody had suggested this, and I converted to. Remember the factorial example? Yeah, this one. Remember this one? This factorial, I used a helper. This helper is a tail recursion version. Okay. Compiler is smart enough to convert that one to, with the help of a helper function, to make it a tail recursive case. Okay. 1+. So how would I do that? How would you do? Okay, exercise for you. It's kind of hopeless. You are not going to do it, but I am going to. Since I am recording this, and people told me that people from the other universities are watching these, so maybe they will do it. Convert this int f int k. Okay. Just a dummy base case. Just a dummy base case. If 0 is 1, return 0, otherwise return 1 plus fk. This is not here recursive, right? The last thing is going to be done here is plus. So write the helper function to convert this function to a tail recursive function. Okay, you can write it. So compiler is doing that. Okay, compiler is doing that. This is smart enough. Okay, so let me move on. So we talked about this at the end of the chapter. At the end of the chapter, we talked about the Stack Overflow and the dangers of the Stack Overflow. Again, read about it on the internet. Why Stack Overflow is so dangerous and how we can prevent it. Okay, and some people say that don't use C programming language, and that would be stupid. Okay, just because C is causing this problem, I mean, just because C is powerful doesn't mean that C is at the C is the guilty one. It is not C, it is the programmer itself. Okay, if you write your code defensively, if you write the right code, okay, use the right libraries, and don't ever let this kind of stuff can happen to your users. Then these kind of problems can be handled in the C too. Okay, it's like pointers are so error prone. If you don't use the pointers, there will be very nasty errors. Yeah, that's true. So don't use the pointers. That's not a good suggestion, right? Read about this. Okay, we talked about recursion versus iteration. Whatever you do with recursion, you can do it with iteration. Okay, sometimes it would be so long. So sometimes it is, for example, remember that give me the depth of this tree. With the recursion, it is just 4 lines of code. If you like to do this with a loop-based function, it's going to take you at least 50 lines. Okay, because basically you have to implement the idea of stack. Without the stack, solving this is not that easy. Okay, so it is easy to convert most of the recursive function to a loop-based one. Some of them are not that easy. Okay, some of them are not that easy. But sometimes the opposite is not easy either. So if there's a loop-based function converted to iterative one, it is not that easy sometimes. So we are not saying that always use recursion or always use iteration. Depends on your case. Okay. So we talked about this kind of stuff. Yeah, okay. I'm not going to write the power function. We already know how things, okay? So thinking recursively is important, okay? Forget how stack works. Of course, you shouldn't forget it indefinitely, okay? Forget for now how the stack works. It's like using the vector class. Forget how the pushback works, okay? The important thing, what the pushback does, okay? Pushback adds an element to the end of the vector, that's it. Okay, you don't talk about the allocation, deallocation stuff. Forget how the stack works. Okay, forget how the suspensions and everything works. Okay, this is an abstraction principle again. And what you do is just, where is my base case? Okay, make sure that you have a base case that you can solve it very easily. And then for the rest of the problem, if the base case is not valid, what you're gonna do is how I am going to divide the problem into smaller parts. Okay, these smaller parts should be exactly the same as the original problem. Okay, but it should be smaller. And if I keep dividing my problem into smaller parts, I should hit the base case. Okay, solve these smaller problems. Sometimes solving these smaller problems will solve automatically the larger problem, but sometimes from each solution you get your results and you need to combine them, like the result from the depth exam. You ask your children their depths, what are your depths? You get them and you choose the maximum one and you add 1 to it, okay? So you apply a simple procedure to the solutions and then you should be done. So 2 things, base case and recursive case. and they should be all there, then you should be fine. And once you do that, okay, check three things. No infinite recursion. So no infinite recursion means that you have a base case, and your making problems smaller reaches the base case. Okay, stopping base cases are correct and recursive cases are correct. That's what we are doing with this, okay? This is one thing that we have, okay? So I mean, when it comes to the factorial, I divide my problem into two. Factorial I minus 1 times I, right? I can divide my problem into 3. Calculate factorial I minus 2, right? And multiply it with I minus 1 and multiply it with I. I can do that too, okay? There is no single way of dividing your problem into smaller parts, and this is one way of doing that too. But for that one, I need to make sure that my base case can handle both 0 and 1, right? My base case should handle both 0 and 1. Why? Because I am calling factorial I minus 2, right? If your base case can handle only 0, not 1, okay, in that case, you will not hit the base case all the time. You are going to hit the base case half the time, okay? You are going to hit the base case half the time. It's like this. Integer factorial int k. If k is 0, return 1 and return k times factorial k minus 1 will work, no problem, but this will not work. Why? Because k minus 2, yeah, it just makes your problem smaller, exactly the same problem. But this, if you keep subtracting 2 from your k, sometimes you are not going to hit k is 0, right? Sometimes you are going to hit k is 1 and k is minus 1. Sometimes you are going to hit k is 0. So to prevent this, what should I do? Okay, what should I do? If I do this, k minus 1, again, I have the same problem. Maybe I should do this, less than or equal to 1. Okay? How about this? How about this? I like to do k minus 3. Tell me, what should I do? Of course, I should multiply it with k minus 1 times k minus 2. So what else? Does this work? Am I doing the, okay. Stopping cases return correct values and no infinite recursion, okay. Is this a correct program? It's not k minus 1, it's not k minus 2, it is k minus 3. It looks like if I multiply, okay, to calculate the n factorial, if I do n times n minus 1 times n minus 2 times n minus 3 factorial, this should work, right? Would this work?
No.
So what should I do? What is the problem? What is the problem in terms of recursive thinking? What is wrong?
N should be greater than or equal to 3 here. 2 factorial is 0.
2 factorial is not 0.
But this will calculate it as 0.
No.
We
It will be even worse. It will be If I say 2 factorial is going to be 2 minus 3 minus 1, it's going to call the factorial with, yeah, so, yeah, you are right. This is, k is less than
Yes.
or equal to 1, it's 1, yes. It is, it's not going to be infinite recursion, but it will be bad, right? For, sometimes it will work okay, sometimes it won't. So what should I do? Maybe I should do, what's your solution?
3.
I think my solution should be if okay, if k is to return 2, right? If k is less than 1, that means 0 or 1, it returns 1. Okay, so I have 3 base cases now, because I am doing this 3 by 3. With the induction, you should do the same thing. Okay, that's why they tell you. Okay, that's why they tell you to solve a few cases, small cases, 1, 2, 3, etc. So sometimes with the induction, you say that assuming that n minus 2 k is equal to n is equal to k minus 2 is correct. I'm going to prove now k is equal to n is equal to k. Okay, that will work too. So why am I talking about this? I mean, checking the base case and no infinite recursion sometimes will require some careful thinking, and don't ignore that. That's what I'm saying. Okay, let's move on. Did I do this with yourself or okay? Yeah. I think I did this last year, so my handwriting is better. It looks like I was using a straight tablet or something because I didn't write this diagonally. Anyway, we did that. Okay, so it looks like, yeah, I use this tail recursion case, a helper function strlen2. Good. So we talked about tail recursion, and mutual recursion is this. Okay, mutual recursion is this. F is calling G, G is calling F, and F is calling G. Okay, this is again recursion. You wouldn't say this is not a recursion. This is recursion because at the end, okay, who is calling F? F is calling F actually through G. G is calling G through F. Okay, this is called mutual recursion. So the same rule applies actually, and there is one example from the book maybe, or from somewhere else. I don't know where I got this, but let's look at this one. Okay. Recursive program to determine if a string has even number of ones. Okay. So if my string is, okay, 1, 2, 3, 4, 5, 6. There are 6 ones in the string. Okay. So that means I should return true for this one. So I am going to write this function, 2 functions, even number of ones and odd number of ones. Both of them will take a string. And let's look at the definition of the even number of ones. It says that if the length of the string is 0, okay, then I just return true because 0 is an even number, right? That's it. Okay. So this is my base case. How about this one? If S0 is 1, that means what? I should return odd number of ones, okay, odd number of ones, substring 1. That means S plus 1. So it means, I think this is the case. I know that this is a 1. Call odd number of ones on this one. If there are odd number of ones in this string, I know that there is one more, so I will return true, right? Because this one will return true, right? This one will return true. And if my S0 is 1, then I will return true, okay? If this first one is 0, okay, and the rest is like this, whatever they are, I say that if this one is 0, I will call even number of ones on this rest of the string. If it returns true, then I will return true. Okay, if it returns false, I will return false. Okay, so this one is calling odd number of ones and even number of ones, so both of them are being called. Is this a tail recursive function? It looks like it is tail recursive here, but it is not that tail recursive there, right? Because it has two recursive cases. Okay, but if the compiler is smart enough, it can convert this to a tail recursive function. If the compiler is smart enough. Okay, so odd number of ones is doing this. If s length is 0, then it just returns false, because if there is nothing in the string, then there is no. It is the number of ones is 0. 0 is not a even number. Returns false. If s0 is 1, okay. If s0 is 1, I just call even number of ones, because in that case, if the rest of the string has even number of ones, if the first one is a 1, then I should return true, and the same case with the other one. Okay, so mutual recursion example. You might say that why are we doing this? I mean, I could have done better by just writing a simple recursive function. Yeah, that might be true. Try it yourself. Write a single function that returns true if there are even number of ones inside the string. Okay, and that's basically it. Okay, that's basically it. So this is mutual recursion example. Okay, and we are going to look at this binary search. And binary search, for that I am going to load the examples from the book. I am just wondering what happens with this if I use just a single level of optimization. I don't know. I mean, O1, O2 may crash for this one. Okay, let me go to chapter number what? Chapter number not 11, but chapter number 12. Was it 12?
13.
I skipped 12, right? Yeah, 13. Let's go to chapter number 13. And load all of them, because I don't remember which one is which. Okay, this is one we talked about, right vertical. No problems. We talk about, again, right vertical. Oh, there's a for loop in there. I don't want to do that. This is power. Okay, this is even number, odd number. Search, yeah, I'm trying to look at this one. Okay, so search is a function that will take an integer array, okay, and it will take the starting address of the index. I like to search inside this array starting from the index number 0 to index number n, okay. And I like you to find the number named key, okay. This is the key to search. I am going to look for this key, and if the result is found, then mark it as found with this boolean, pass by parameter, pass by reference, and give me the location to as an integer. So I am going to return two things. If I found it, okay, I will make this boolean true, and if I found it, I will return the location. If I don't find it, found will be false and location will be meaningless. The better implementation would have been returning an integer. If I find the result, if I find the key, I would return its position, otherwise I would return -1, right? I didn't have to use this fancy stuff here, okay? So this is how we are going to use it. Using it is very easy. Okay, this is just search, so that's what I'm going to do. I have an array size. What is array size? It's 10. I am going to fill this array with these numbers. AI is 3i, and I print them out, okay? And if it is found, I will print this like that, okay? If it is not found, I am going to say that I am not going to find it. By the way, as you have noticed, this array is a sorted array because the search, binary search, works with sorted arrays. That's the algorithm. Let me show you the algorithm. That's the algorithm. Algorithm is this. If I have all these numbers, 1, 7, 9, 10, 20, 27, 31, 57, okay, I like to make a search for, let's say 27, okay. Since this array is sorted, this is what I am going to do. I am not going to look at the numbers one by one. I'm not going to say that, let's check the first one, then the next one, then the next one, then the next one. No, I am not going to do that. I will just look for the middle element. If it is the same as 27, then I find it, okay. If it is not, then I will compare these two. Is 27 larger than 10? Yeah. Then I will ignore this part of the array. I will ignore this part. I will look at the second part of the array, starting from this part. So now this is my place to look at. What is the middle element is here. Is 27 is equal to 27? Yeah, so I found it, okay. If it is not, then I will continue this process until my arrays becomes an array of size 1, in which case I know the solution. So the problem every time, okay, this is a large array with like 10 elements, but the second time my array becomes array of 5 elements or 4 elements. Third time my array becomes array of 2 elements, and it goes that way. So every time I am making array smaller, okay, and I know that I am going to hit the base case, because what is my base case? My base case is this, okay. I have a single element in my array, and it is not equal to the number I am looking at. This is one of my base cases, okay. In this case, I am going to return false. The other base cases, the number in the middle is same as my key, okay. In that case, I am going to return true and return the stuff. Okay, so that's what we are going to do. That's what this program is about. And let's look at this implementation search, okay, binary search. But before that, maybe I should take 10 minutes of break. After the break, we will continue. Okay? Good. See you in 15 minutes. 15 minutes. Let's be here around 9:30. Ya yoklamayı unutmuşuz. Geldikten sonra unutturmayın bana yoklamayı.
Notlama kağıdı burada mı?
Bilmiyorum da daha doldurmadık.
Öyle mi? Ha, tamam. Burada hangi ders var? 241.
Daha dağıtma, imzalama.
Efendim?
Daha dağıtma, imzalama.
İmzalamayayım ben.
Daha
Çıkacaktım.
yeni mi geldin?
Çıkacaktım dersten de o yüzden.
Ha, çıkacak mısın?
Hı hı.
Yeni geldin.
Sorun olmaz herhalde.
Bilmiyorum. Ben yeni geldim söyleyeyim.
Onu hiç sormaya gerek yok bence.
Aynen arkadaşlar.
Hayır çok kısaydı ya dedim ki şöyle de olabilir belki dedim. Çok gereksiz bir detay olduğunu fark ettim. Olmasın belki.
Okay, let's look at this program. Do I have enough juice? Yeah, okay. My program is here. Yeah, this one says that first I'm going to calculate this the mid element, okay? I did not calculate it yet. But as a first base case, is first is greater than last. That is, if some reason, maybe because of the recursion, maybe because of something else, okay? If first is greater than last, then I should return a false, okay? Found is false, and don't get into any recursion, and I just return it, okay? That's it. That's what I do in this case. So this is one of my base cases. My found is false, okay? Otherwise, this is what I'm going to do, okay? Since first is not greater than last, at most it could be equal. So I am going to calculate the mid element, add both of them and divide it by 2. This is mid. And if key is same as a mid, then found is true and location is mid. That's it. So this is my second base case. This is my second base case. I handled it. Otherwise, if key is less than a mid, middle of the array, then I am going to call this search. I am going to call this search, okay? This way, I will say search the array A from first to mid minus 1. Why mid minus 1? Because key is less than a mid, right? So I am going to search the first part of the array. Key and found location will be there, okay? If key is greater than a mid, then I am going to do this. I am going to search the array A from mid plus 1 to last, okay? Is this a tail recursive function? So what is the rule for the tail recursion? If the last executable statement is the function call itself, it is tail recursive. In this case, yeah, other than the base cases, yes. This is a tail recursive function, and it works that way. I didn't like this function because I don't know why they are doing this. Let's convert it to the right one, the correct one. Let me copy and paste it like this, and I will return an integer and get rid of the stupid stuff here. Okay, so it should be like this. I am looking for this integer, and I will return. If I found the result, I will return the index. If I don't find it, I will return -1. So if first is greater than last, I will say return -1. Okay, so that's one of my base cases. I don't like these parentheses, single statements. Parentheses I don't like, and then int mid should be here, not there, because it's local to the scope, right? First plus last over 2, yes, that's true, and I get this comparison. If key is equal to a mid, then I solved it, I found it. So what am I going to do? I am going to just return mid, right? Okay, so that's it. And then after that, I am going to call the search function. Okay, and I don't need this if actually, right? I mean, if either is less than, if they are the same, return mid. If k is less than a mid, do this. Otherwise, I don't need the third if. Otherwise, do the search and get rid of both found and location. And again, I don't need these stuff. This is much better. What is okay? They put lots of stuff in there, so. Okay, so that's it. Oh, okay. How about this then? I mean, without, sometimes the compilers, okay. So this is the problem. Nobody's telling me the problem here. Return and return. Okay. Sometimes compilers will give you an error message or warning message at least saying that this function should return something, but it is not returning anything right here. But if you look at my, thank you, if you look at my if cases, there is a return here, and for these if cases, there is a return after each possibility, after each branch, so I should be fine. And this is definitely a tail recursive function search. Okay? So it is both efficient in terms of, I mean, it's just halving your problem. I mean, it's not going one by one. So if your array size is 1024, in second function call is going to be 512 and 256 and 128 and 64 and etc. So it is doing, every time it is doing half of it. Okay, so it is very, very fast. It is very, very efficient. And it doesn't use stack space much other than the first function call because it is tail recursive. So you are doing something very efficient and something easy to look and easy to prove that this works. Okay, so recursive and efficient, best of both worlds. That's somebody had a question? You had a question?
What we are trying to find -1.
What is it again? What
we are trying to find -1. If first bigger than last, we are returning -1. But what if the middle is -1?
Well, mid cannot be -1.
It is positive notation.
Well, I mean, if first is greater than last, okay, then I'm going to return 1. And I know that first and last are always positive
Okay.
integers, right? If you divide them by, yeah.
Sorry, I missed that.
So you are confused about the index and the content of the array.
Yes.
And content of the array could be anything. I mean, it could be, I am not returning the found value, I am not returning key. I am returning the position of key. Good. Okay, so that's the end of the chapter. Recursion is important. Try to write recursive programs. I think now we are doing face-to-face exams in the finals. And remember, I usually ask one question that I will ask you to write a function, and in the midterm I write the same thing too. I think in the finals you will have a question about recursion, a recursive function, write a recursive function, something like that. So don't forget to search for all the exam questions from the previous year students. Okay, they keep nice database of the previous year's questions. Okay, I used to give them myself to you, but if I give you the previous year's exams, nobody will study them. I figured, because it is worthless since I am giving you. But if you find it from somewhere else, it becomes valuable. That's why I gave up giving those questions. Okay, so let me. Okay, if there are no questions, let me see if I skipped anything about this. Checking the recursion and doing this stuff again. Nice display here. This is my array, and mid is this one. And if my key is 63, then I am going to look for here. Then okay, so if I have 1024 elements in my array, okay, I will call this function 10 times. Why? Because 2 to the power is 10 is, okay. So every time I'm dividing it by 2. 512, 256, 128, 64. So down to 1. So there will be 10 calls. By the way, at each iteration, at each function call, I either search this one or that one. I am not calling both of them. Okay, I am not calling both of them. Some algorithms, they do that. Okay, every time they make a recursive call, they do 2 or 3 or 4 recursive calls. Okay, at the same function calls. Those kind of functions are very, very expensive. They cannot be implemented using the tail recursion, and they are very, very expensive because every time, it's like a tree, right? Tree. Okay, let's look at this one. Let's say you are playing chess. Okay, in chess, there are satranj. Okay, there are 8 by 8 cells. Okay, 64 cells. Or maybe now, why are we talking about chess? Let's talk about your peg solitaire. Okay, in your peg solitaire, okay, like that. How many opportunities, how many possibilities are there at the beginning of the standard peg solitaire stuff? There are 4 of them?
4.
Yeah. So you would say either possibility 1 or 2 or 3 or 4, right? So after 4, maybe there are 4 of them again. Okay, 1, 1, 1, 2, 1, 3, and 1, 4, or maybe even more because you are making up more space, right? So at the first place, at the first level, you have 4 possibilities. Then for each one, there are 4 more possibilities. So on the average, let's say it is 4 possibilities. So if my game takes 10 levels, it is 4 to the power 10. Okay? There will be 4 to the power 10 possibilities at the down level, top bottom level. And that's a very big number, actually. That's a very big number, right? So this one is very big number. And for each of those numbers, there's an activation record. Activation records are, I mean, depending on recursion, are going to be expensive. Probably this will not fit into your memory. Okay. So if you try to do this kind of, what is the maximum number of plays that you can do with this board? If you ask, I have to ask to each of those, right? Each of those, and that would be a very, I mean, smart thing to write, because I just wrote it. I don't have the memory resources or the CPU resources to calculate it. But in terms of memory and CPU, it is too expensive. Sometimes, I mean, if you do this kind of recursion, it becomes very expensive. But if you do this kind of recursion, smart recursion, tail recursion, and single recursion every time, it is as efficient as writing a loop. Okay, good. So we talked about this and efficient binary search. By the way, if I try to draw, let's say this is the number of elements in my array, and this is the time of execution, okay? Let's say with 10 elements, I measured the time, it took 10 milliseconds, okay? For 100 elements, how many seconds do you think it will take for 100 elements? If for 10 elements it took 10 milliseconds, for 100 elements, how many milliseconds do you think it will take? 100? Linearly 100, but this is not going linearly, because 100 is going to be much more efficient. Why? Because I am just dividing it by 2. It is not like 10 times 10. So probably I would expect 20. Okay, 400 it is 20. 4,000, okay, it's going to be 30, somewhere like that. Okay, 30. So my curve will be like that. We like these kind of curves because this is a log n curve. Okay, we like these kind of algorithms. You increase your number of inputs, your runtime doesn't increase linearly. Linear increase is like that. Okay, just a straight line. Okay, you increase your number of elements, your runtime increases proportionally, linearly proportionally. This is not bad. This is much better. We like this one. Well, the best one is this, actually. The best one is this. Whatever you do, your execution time is the same. Okay? we like this one. Let me try to make it more parallel to the, okay. It always takes 5 milliseconds. That's it. We like this one best. If this one doesn't work, we like this one. If it doesn't work, we like this one. And there are other algorithms like this one. Okay. These are, okay, this is n square. Sorting is something like that, n square. Okay. Remember the bubble sort? It is n square. And there are even worse ones. It's like this. It is n factorial. Okay. You increase like 10, your runtime becomes 10 factorial. 100, your runtime becomes 100 factorial. Memory is not an issue, it is the CPU time. Okay. Usually with that kind of algorithms, you don't implement those kind of algorithms. They are too expensive. I mean, for practical problems, your CPU time will be like a few years, 100 years, 2,000 years, if you calculate them. So you will do this kind of analysis next semester with your data structures course. So you will try to find solutions around here, here, here, and sometimes there. But this one we won't like, okay? But we should be able to know if our algorithm is like this too, okay? Which one is worse, n factorial or n to the n? Of course n to the n, right? Because this is multiplying n number of n's. This is multiplying n number of consecutive numbers. So, but for us, they are both equally bad, okay? We don't implement those kind of stuff. That's why before implementing an algorithm, you do this analysis. If the analysis is right, you start implementing it, okay? As I said, the algorithms that you have learned last semester, bubble sort, sinking sort, and insertion sort, they are all n square. The algorithm that I talked about yesterday, remember that merge sort? Merge sort is somewhere here, okay? It is n log n. It is worse than n, but it is better than n square. And this is the theoretical limit. You cannot do better than n log n for sorting of unrestricted integers or the real numbers. Okay, good. So this chapter is over. Recursive solutions. As an exercise, okay, almost all the string functions that you have learned in C, okay, they all can be implemented using recursion. Just implement them using recursion. String compare strcmp or str and copy, okay. Think about this one, strcmp. What are your base cases for the strcmp? Remember, compares two strings. If they are equal, return 0, right? I think my base case would be if both strings point to a null character, just return 0, right? They are just pointing to the null character, okay? They are pointing to the null character. If the first character of the first string is greater than the second one, return +1. If it is less than, return -1. If it is equal, then if the first character is equal, what would you do? If two first characters are equal, continue checking. So call it recursively. So if this is the case, A, B, C, D, and this is A, B, A, right? So these are equal, just continue. Here I should return, if C is greater than A, it comes later, so I should return a -1. So by looking at the first character, you either make a decision. If it is null character, then return 0. If it is one of them is greater than the other one, return +1 or -1. If they are equal, other than the null character, then continue, make a recursive call. Okay, so easy to implement. Just implement this strcmp str copy, str cat, okay, all the strlen, all the string related stuff. Okay, good. Any questions about the recursion? Okay, if there are no questions about recursion, I will start the new chapter. It is called inheritance. Where is my inheritance? Oh, I don't have the inheritance chapter here. Recursion, inheritance. Yeah, it is here. Okay. So, with the inheritance, we will introduce one other object-oriented programming fundamental concepts. We looked at the encapsulation along with the abstraction. These are very important. We have been talking about them. Okay. And inheritance is the third, the fundamental principle of object-oriented programming. Then will come the polymorphism. Polymorphism depends on inheritance. Without inheritance, there is no polymorphism. Okay. We are going to look at the inheritance first. As always, okay, our main purpose is code reuse, generic code. If you write generic code, that means that that code is reusable. It is not specific to your project, okay? It has a clean interface. It can be used over and over again for other projects, okay? And inheritance is very useful for writing reusable clean code. That's what we are going to do in this chapter. So let me go back to, what is this? I think this one is doing the same search with a while loop. Okay, that's why they chose this stupid interface, because they kept saying found true and etc. Okay, I'm going to close them all. Let's close them all, and let's go to this chapter.
Teacher,
Yeah.
Isn't it while one more efficient in terms of memory?
No, because as I said before, that search is a tail recursive search. It is as efficient as a loop implementation in terms of memory and in terms of CPU usage. Okay? Because it is, your compiler directly converts it to a loop version with the appropriate flags. Okay, let's open this one, source code, chapter number 14. Okay, in chapter number 14 we have these classes, and this one and this one. Let's open these. I have this nice employee class. I have my header file. Employee class is this. Okay. For the private part, I have my çalışan, employee çalışan in Turkish. I have the name of the employee, social security number, that is kind of TC kimlik numarası. And I have the net pay, okay, how much money I am paying to this employee, okay, net pay. And these are my public functions, nice constructors, no parameter constructor, and name SSN, so I don't take the net pay. So getters for the name SSN, and get net pay will return something, set name, set SSN, set net pay, and print check. Okay, the print check is at the end of the month or at the end of the week, I print a check to give my employee, okay, this is how much money you made, and go get your money from the bank with the check. Okay, that's what we are going to do. And the implementation is very simple, actually. That's what we are going to do, okay? Employee, no name yet, no number yet. Stupid decisions here. I mean, if you make the name of an employee no name yet, No name yet becomes his name, right? So this is not a very good way of doing stuff. I mean, and at least you would have said Ali Yilmaz or something like that. Everybody knows that Ali Yilmaz is a kind of a generic name in Turkish. Okay, net pay is 0. For the constructor, that will take the name and the number. I am just using the member initializer syntax position, name, the name, SS and the number, and net pay is 0. Setter, getter, okay. Get, set net pay. For the print, it doesn't know what to print, because to be able to print something for an employee, I need to know what the employee does. I need to know how the employee wins his money. Okay, if I am paying the employee the fixed salary every month, that says salary of the employee. If I am paying the employee hourly by the hour he works, that becomes an hourly employee. Sometimes I pay my employees by the commission. How much good did you sell? I sold like hundreds of this machine and hundreds of that device and etc. And I give a commission to that employee. So for the print check function, I don't know what to write on my check. That's why the book says that I am going to terminate the program, because print check doesn't make any sense for this employee. Okay, why did you write it then? It will be clear in a few minutes. Okay. So employee is kind of a class. It's a nice class, but it is not supposed to be used directly, because there is no such thing as simple employee. You have either hourly employee or salaried employee or commission employee and etc. Right? Different types of employee. Let's implement one of these employees. Salaried employee. The salaried employee is very similar to employee. Okay? It has both name, SS, and net pay and salary. Okay? Salary is weekly salary. How much money I am paying to this person. Okay? And I'm going to calculate net pay by looking at the salary. So this net pay of this person is going to be the salary. Okay? So when I say print check, it's going to look at the salary and say that, okay, you are a salaried employee, I am going to pay this much because you are making this much. Other than that, this one, and I think all these functions are exactly the same as the employee class. I have two more functions, get salary and set salary. Other than that, the rest of them are the same. Of course, I have to write new constructors because this is a different class, right? And I added one more data member. And to be able to implement this class, actually, all I would do is just copy paste from the employee class and modify things and add these two functions, get salary and set salary. And my print check is, okay, is more meaningful. I just say my salary is this much, okay, set net pay, and I say pay to the order of this person, just a standard American check, okay, the sum of this much, okay, employee number this much. Let me show you one, because this is so common in US paycheck images. Let me show you a paycheck image. Yeah, for example, this one. This is your first paycheck, okay? So this is the printed paycheck. It says that pay to the order of pay against the check, current name, etc. Okay, and you give the name, you give the money, and etc. All the things. That's what we are doing here, actually. That's what we are doing here. I am just writing all of that stuff. Okay, so this is more meaningful. But the thing is that I have my employee class, and I am writing all the other things. See this dot dot dot? That means that it is same as the employee class. So copy pasted, change all the employees to the salaried employee. Okay? So we don't like copying and pasting and modifying. Okay? Why? Because if I have a problem with the employee.h or employee.cpp, I will just make that problem worse by copying and pasting. That's one thing. Even if I don't have a problem in employee class, if I decided to make a change in employee class, now I have two places to make change, right? In employee class and the salaried employee class. Inheritance says that there is a solution for this. Of course, there is much more to inheritance than this, but at the beginning we always say that. We say that inheritance, there is a solution for this. Use this mechanism, okay? Salaried employee, and this one, let me open those. This is my new salaried employee. Just pay attention to this syntax. Say that salaried employee is an employee actually. I am the same as class employee. Okay? I am the same as class employee. The only difference is I have two more functions here. Get salary and set salary. I have one more data member, private data member. And I don't like how the print check works. I am going to change it. Of course, I need to define this constructor, these two constructors. Okay? So that's it. In a way, I am writing a new class on top of class employee. Class employee is a different class. I am saying that as a salaried employee, I am the same as class employee, but I have some differences. I have some additions. I am inheriting all the things from class employee, but on my inheritance, on top of my inheritance, I will add this private data member, I will add these two functions, and I will modify this print check function because I did not like how it worked. Of course, as a class, as a standalone class, I need to define my constructors, of course. Okay, so that's a perfectly valid class definition, and that's what we call inheritance. Kalıtım in Turkish, miras alma in Turkish. So we inherit all the assets of this employee class, and but don't get this wrong. Employee doesn't die. Okay, it doesn't go away. It just stays as a standalone class. It works. You can make the objects of employee. Employee is a standalone class. In fact, employee doesn't know that salaried employee is inherited from employee, right? Employee doesn't know about that, okay? Salaried employee says that I am same as class employee, but I will add new features to it. Some private data members, or you can choose to add public data members too. And I will add some new functions, and I modify some of them. Okay. And let's see the implementation of this salaried employee. So instead of, see, salaried employee used to be like this crowded, and most of them are copy pasted from employee class. Now it became so simple, yet understandable, because this one says that I am an employee. Okay. There is a relationship between salaried employee and employee class. Is a relationship. Let me write it somewhere. There is a relationship. Previously we had has a relationship. Remember composition? Remember the holiday class? Holiday class has an object of day of year class, right? There was has a relationship between holiday and day of year. Now there is a relationship between the salaried employee and the employee. Okay, so I defined is a relationship between them. Both of them are very powerful. object-oriented programming techniques, and both of them are encouraged for you to use. Okay, let's look at the implementation. Implementation is very simple too. Okay, I include salary the employee.age. By the way, salary the employee includes employee age, because the compiler has to know what employee is, right? So I include employee.age, and the salary the employee is here. Salary the employee says that, okay, this is my constructor. Since I am a employee class, okay, my constructor will call the constructor of the employee here. Okay, this employee constructor will handle the private data members that comes from the employee, which is the name and the social security number and the net pay, right? Okay, and for salary, since salary is new, I am going to set it myself. How about the other one? See, the other one takes the name, social security number, and new weekly pay, three parameters from the customer. I will send this name, the name and the number, new number, these two. I will send these two to the employee constructor, but I will handle this new weekly pay myself. Okay, good. So get salary and set salary are very simple, and print check is this. Okay, print check is like we did before. So total of 49 lines. The rest of them will come from the class employee. Okay, again, this is called inheritance. It is one of the basic principles of object-oriented programming. Try to use inheritance whenever possible. So how are you going to use inheritance? Well, it doesn't make much sense if you have just two classes. One of them is an employee, the other one is inherited from an employee. It is usually more, and we are going to use more. Let me show you what we are going to do. We are going to do this. Okay. This is my employee class. Inside my employee class, this is a UML diagram. UML diagram, okay? Okay. Unified modeling language. You say that I have a class employee. Inside my class employee, I have my data members. Minus me is private, okay? I have string name, SSN string, pay, double, and these are my public member functions. Employee constructor, second one, get name, set name, and etc. So this is my employee class, and salary the employee, using the is-a relationship, inherits from the employee class. Okay, I have one private double salary, and I have the constructor, and I have the getter setter for the salary. Okay, this is salary the employee. Another example might be hourly employee. This employee will get their money, his or her money, by hourly work. How many hours did you work? 10 hours. What is your rate for hour? $15, etc. So this is hours, how many hours, and this is how much per hour. Okay, so my constructor again, set get for the hours, set get for the wage, and print check actually do the same thing again. So this is my hierarchy. This is called the hierarchy in Turkish. This is my hierarchy. In my hierarchy, I have the employee class, and I have the salary the employee inherited from the employee. I have hourly employee inherited from the employee again. Okay. If you like to use composition that has a relationship, you can put you can put a day of year object inside this employee, and this becomes day of year becomes your part of your employee as they're using it has a relationship. Has a relationship is used using this is shown using this diamond sign. These are arrows. This is the direction of the inheritance. Direction of the inheritance. This diamond shape shows there is a composition or has a relationship between day of year and employee. Okay, we don't have it in this case, but I mean, you could have it. And these are UML diagrams. It's kind of a standard diagram to explain the relationship between classes. C++ people use this. Java people use this. Any object-oriented programming professional or practitioner use this kind of a diagram to show the relationships between the classes, composition and the inheritance. Okay. Good. So I'm going to show you the hourly employee. Let's look at the hourly employee actually definition. Let's look at this hourly employee. Okay. Let me load it up. Where is my hourly employee? Hourly employee and hourly employee. Open them. Okay, this is my hourly employee. It derives from employee again. It adds two data members, wage rate and hours. 10 hours at $20 per hour, etc. My constructor is a little bit more crowded. Name, social security number, wage rate and hours. Setters and getters for them, and print check again will be redefined. Because we don't like the print check of the employee class. I don't like my inherited function, so I am changing it. Okay? I am changing it. Good? So this is what inheritance is about. Let me go back to this picture and let's talk about some terminology. This employee class is my base class. Okay, in C++ we call these classes base classes, and this operation is the inheritance operation. Okay? We derive a new class out of this base class. Okay? Derivation, we derive a new class. Okay? Türetme. Temel sınıf, türetilmiş sınıf. And this operation is called derivation. It's like the derivation of the calculus, türev. Matematikte türev vardır ya. Türev aldık, türevi, bunun türevi. So this is derivation. We derived a new class from the base class. Okay? This is the derivation operation. And if you derive a new class from the base class, you created this is a relationship between these two classes. If you compose day of year with this one, you have has a relationship. Okay? Has a relationship between them. This is a relationship is very is special because compiler knows that there is a relationship between salaried employee and employee class. What does that mean? If I need to send an employee parameter to a function, since there is a relationship between them, it is okay for me to send a salaried employee to that function. Because every salaried employee is actually an employee, right? Because there is a relationship. If a function needs an employee pointer, I can send address of a salaried employee object to this function and it works. Because there is a relationship between them. Each salaried employee can behave like an employee. Why? Because I have inherited everything from this employee class. What does the employee have? It has set name, get name, set SSN, get SSN. Salaried employee has the same things too, right? So that's what we mean by is a relationship. Okay? So is a relationship is special. Compiler knows about it, and we are going to use this feature a lot in our programs, in our libraries, and that will be very useful, and as you will see, in implementing some professional libraries. So we talked about some terminology. People always ask this kind of questions. Is it possible to make inheritance from another class? And again. Yes. Let's say I have a motor vehicle as a base class. Automobile and motorcycle are derived from this base class, okay? And then I have convertible automobile derived from the automobile, okay? So this is possible. Inheritance here and inheritance there, okay? Every automobile is a motor vehicle. Every motorcycle, each of those motorcycles are motor vehicles. And every convertible is actually a automobile, which in turn is motor vehicle. Okay? Good. So these kind of things are possible too. What do I have in here? Okay, I'm not going to, because I don't have time. Maybe I will continue on this on Monday. Okay, any questions before I stop? Yes.
It is similar to inner class. And what is the different inner class?
Inner class is a case of composition. There is no is a relationship between them. Okay? There is no is a relationship between your outer class and inner class. It is a case of composition. Here, there is an is a relationship. Compiler knows that your salaried employees are actually can be considered as employees. With the inner classes, you don't say that all of the outer class data members and the functions are mine too, right? You don't say that. Your inner classes are standalone classes. Okay? They can be used if they are public classes separately from the outer class, and you can separate them. But with the inheritance, salaried employee has to behave like the employee because it derives from there, and salaried employee has to have this set name, get name functions. Okay? Related but completely different. Okay, any other questions?
I have one actually.
Yeah.
Can we go back to the definition of salaried employee?
Salaried employee, implementation or the header file?
Header file.
Yeah.
What is that public for online sourcing?
You mean this?
Yes.
Well, ignore this for now. I mean, just syntax. I mean, today about the inheritance, I already told you this. Only addition of this syntax. Ignore this public for now. It can be private and some other keywords in there, but we will never use them, and they are not that important for us. So this is how you do the inheritance in C++. You say that I am defining a new class. I am deriving myself from this employee class, and this is my definition. These are my additions to the employee class. That's what you are doing. So just memorize it and ignore the meaning of public for now.
If I change that public into private, does that change the behavior of the class?
Yeah, well, as I said, ignore it. Don't talk about it, and don't do that. Okay? So it doesn't become an inheritance anymore if you make it private. Yes.
Do we have to use the keyword public or private?
Yeah. Well, you don't use anything other than public. Okay? Any other questions? For some reason, I always get this question. That's why as soon as people see public, then how about private? Public doesn't mean this public. The meaning of this public is very different. And we don't use anything other than public for inheritance. If you use something else, it becomes something else. Okay, good? Yeah.
When we are in main function, in this example, we don't use employee class.
Well, that's a good question. Actually, I did not show you anything. Yeah, maybe I should show you.
Use as copy pasting.
Yeah, let me show you one main function. Maybe this one. Yeah, this is your main function. Okay, you include hourly employee and salaried employee. Okay, you just include them, and you make an hourly employee Joe, and you make salaried employee boss. That's it. I mean, you use these classes as regular C++ classes. You don't talk about using inheritance. You don't talk about doing this and that. Okay? You just use them. So since I defined both of them inside this namespace savage employees, I had to do this separate using declarations. Okay, using this. Then I can use this hourly employee and the salaried employee regular classes like day of year, holiday, etc. Okay, and employee, since employee is included,